Alright, so in this video I want to talk about likely the most important piece of elementary number theory, and a really important piece of math in general, and that's prime numbers. And you've probably heard about prime numbers before. Prime numbers are important because it's like when you want to talk about complicated objects, and you have trouble with that, you often want to reduce them into their constituent parts. And we can do the same thing with natural numbers through what are called the prime numbers, and so that's what we're going to see into this video. So last video we saw studying divisibility in the natural numbers can yield to really useful results, like solving linear Diophantine equations, even though divisibility doesn't actually seem to apply. And so, as I've said, the natural numbers have a very important structure under divisibility that's actually directly related to those so-called prime numbers. So first of all, before we start talking about the prime numbers, we want to talk about the Euclidean algorithm. And so, the Euclidean algorithm is a way to compute the greatest common divisor of two numbers efficiently, and that's the keyword, efficiently, because we want to be able to do things with computers here, and that's actually often a problem in elementary number theory. It's how do we translate a complicated problem into something that a computer can solve. And so, in this case, there is an easy algorithm for computing the greatest common divisor of two numbers. And the reason we're looking at this is, as we saw last video, the greatest common divisor is a great tool for divisibility in general. I mean, it helped us for linear Diophantine equations for one, and it's going to help us for prime numbers as well. So before we talk about prime numbers, we want to make sure we know how to compute them easily. So, like any algorithm, the Euclidean algorithm is separated into steps. And, those steps have to be concrete so that we can feed them into a computer, and a computer can do them. So, we're given two numbers, a and b, that are integers, with a and b not both 0, because if they're both 0, then the greatest common divisor is obviously 0. And so we want to compute the greatest common divisor of a and b. And so we do so by algorithmically following these steps. So if any of a and b are smaller than 0, we set them to their negatives. So let's take an example. For example, if I want to compute the GCD of minus 143 and 369, well, that's actually the same as the greatest common divisor of 143 and 369. And so that's all that this step is telling us to do. We're just switching minus 143 to 143. It's a simple step. So the next step has basically the same kind of meaning, and it's only ordering things around so that the computer can deal with some specific order of our two inputs. So if I've got that a is bigger than b, because I'm computing the GCD of a, b, right? I'm simply going to switch around a and b. That's what I mean here by simultaneously setting ab to ba. I'm just switching this tuple. So in this case, we've got a is smaller than b, so we're not going to switch it. But if we started with 369, 143, instead of 143, 369, then we'd also get to this end input here. And so that's all so that we can talk about the next steps specifically instead of generally if we know we have some ordering on our inputs. That's all that it's saying. So, then we're saying that if a is equal to 0, we return b. What this return means is that we stop the algorithm, and as an output, we give b. So the GCD of a and b would be b. Even though that's often not the case, it is the case when a is equal to 0. That GCD of 0b, that is simply equal to b. Because keep in mind, every number divides 0, right? And every divisor of b divides b, and the greatest divisor of b is obviously just b itself. So, how does that help us? Because we're often not going to start with input 0, and that's where we get to our most important step, which is to reduce the inputs of our greatest common divisor. So we want to make them smaller, all while not changing the greatest common divisor, so that we can keep doing that again and again until one of the inputs reaches 0, and then we have something that we can actually compute easily. So we know that a is bigger than 0 because, we've passed step 3. And so from the theorem that we saw in divisibility, we have that b is equal to aq plus r. Remember, that's our quotient remainder pair, with r bigger or equal to 0 and smaller than a, right? So this is just, the quotient is just how many times A divides into B, and R is the remainder that's left on division. So what we do is we set the tuple AB to the tuple RA, so R is this remainder here, and then we loop back to step 3. So what this is saying is actually that the GCD of A and B is equal to the GCD of R and A. So we're going to prove that because, it might not seem obvious right at the start. But, first of all, let's maybe look at an example of using the Euclidean algorithm to calculate the greatest common divisor of two inputs. So for example, if I want the greatest common divisor of 429 and minus 327. So I can take steps 1 and 2, and I can just switch them around and make them both positive, and that's not going to change anything, obviously. Now we skip step 3, because 327 is not equal to 0. And so now we can perform step 4. So 429 is equal to 327 plus 102. And you can check that yourself. And so now I can set the tuple 327, 429 to the tuple 102, 327. And so now I can loop back to step 3 by the algorithm. So now I'm at step 3 again, and once again 102 is not equal to 0, so we do the exact same thing as before, but now we've got 327 is equal to 3 times 102 plus 21. And so now I can do the same thing of setting that tuple to the remainder and the smallest pair in the first place. And we loop back to step 3. 21 is not equal to 0. We do the exact same thing. You can check all these calculations yourself if you want. But probably better to do them on paper yourself based on the algorithm we had last time. And so we just keep going. 18 is not equal to 0. We keep going. 3 is not equal to 0. We keep going. And now we get 318, 0, 3, because 18 is equal to 3 times 6. And so we've got, obviously, that 0 is equal to 0, so now we return 3 as an output. So the algorithm is done, and we have the greatest common divisor of 429 and minus 327 is 3. And you might want to check for yourself that 3 actually does divide those two numbers. So let's actually prove that this algorithm is correct, because, it might not seem very obvious, and we don't want to use something that's false. So steps 1 and 2 obviously don't impact the greatest common divisor. So, we're just switching things around, and we know the greatest common divisor commutes. And switching the negative sign doesn't change anything about the divisibility of a number. So all we need to show is that step 4 is not going to impact the greatest common divisor. We just want to show that the GCD of A and B is equal to the GCD of R and A, as I said before. And once we do that, we'll have proved the correctness of the algorithm. So let's just label those two. We're going to have D as the GCD of a remainder with A, and we're going to have E as the GCD of A with B. So by definition, we've got that D divides A and that D divides R, because it's a common divisor. So because of linearity of divisibility, right, that we've seen before a few times already, we have that D divides AQ plus R. Now remember, D divides any AX plus RY, and here we're taking a specific case of x equals q and of y equals 1. And notes that AQ plus R is what we have for B. So that means that D divides A and D divides B. So D is a common divisor of A and B, which means that it divides the greatest common divisor of A and B, which is E. So here we've shown that D divides E. We can do the exact same thing to show that E divides D, by simply noting that E divides A, E divides B, so E divides B minus AQ. So the same kind of logic as here, but we're just kind of changing things around, and that's equal to R. So E divides A and E divides R, and so E divides the GCD of R and A, which is D. So we've got that D divides E, and we've got that E divides D, and since we're both bigger or equal to 0, since we're both bigger than 0, and that they divide each other, we must have that D is equal to E. So we've shown that the GCD of A and B is equal to the GCD of N A. And so, it might be a little unintuitive to just look at the proof like this, but it might be easier if you give yourself a few examples to see that the remainder keeps that property of division that B already had, because we've only removed integer multiples of A from B. Try to think about this whole linear combination that has to do with divisibility when you're thinking about this. So it's the best way to think about it. One thing we have to show as well, since this is an algorithm, is that the algorithm terminates. What I mean by that is that if I feed this to a computer, no matter what, it will finish. The computer is not going to keep going on and on and on forever, because we don't want that. Well, I mean, that's a pretty easy proof. After each application of step 4, the smaller of a pair is going to decrease, since R is smaller than A by definition. And since there are only finitely many non-negative integers less than the initial A, then there can only be finitely many applications of step 4. And so that gives also an easy upper bound on the amount of steps, well, the amount of times we're going to apply step 4. It's going to be at least A. It's going to be smaller than A, sorry. And actually, it turns out that in terms of the complexity of this algorithm, we can do even better and get to log A, but we're not going to get into that at all, into complexity of algorithms. That's not what we're going to be looking at in this series. So now we can talk about prime numbers. So let's define a prime number first. And so prime number is an integer p, which is bigger than 1, such that it cannot be written as p equals a times b, with a, b are bigger than 1. So what that means is that the only divisors of p are 1 and p itself. So if I take, for example, the number 6, that's not a prime number because 6 is equal to 2 times 3, and 2 and 3 are bigger than 1. But if I take the integer 5, well, 5 can't be written as 1, 2, 3, or 4 in terms of multiplications of each other, well, except, of course, 1 times 5. So 5 is a prime number. And so note that, if I take any integer, here that's this a here is referring to any other integer that is smaller than p. If I take any integer, none of that is smaller than p, sorry. If I take any integer a, and I take its greatest common divisor of p, that's either going to be 1 or p. And why is that? Well, the divisors of p, as we've seen by this definition, are either 1 or p itself. And since the greatest common divisor is the maximum of the common divisors, and that the common divisors is made by the intersection with the divisors of p and a, well, the common divisors are going to be at smallest 1p, and so the maximum is either 1 or p. And so this actually allows us to partition the natural numbers into either composite numbers, which are numbers that can be written as a times b, or prime numbers, which can not be written as a times b. And then we have the special case of 1 itself, which in some sense is a composite number because it's the empty product. So the first few primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and you can keep going on. Note that the next one after this, you might think it's 33. It's not, because 33 is 3 times 11. It's not 35, because that's 5 times 7. It's 37. That's the next one. And we can keep going. And we'll see at the end of this video, there's a quick way to get all the primes under 100, or under any number for that matter. That's relatively small, when I say quick. So before we get into the most important results on primes, let's first note an important sub-result on divisibility with primes. So that's going to be a lemma that we're going to use later. And we're saying that if p is a prime, and p divides a1 times a2 times ... times an, so this is just some n-fold product of integers, then we must have that p divides one of these integers for some, p divides ai for some I is in 1, 2, all to n. So that just means that p divides one of these constituent products. And you know that we can't necessarily say that for non-prime numbers. So, for example, if I take 4, 4 divides 2 times 2, because 4 obviously divides 4, but 4 doesn't divide 2, or 2. And, similarly, I could take 8 is going to divide 4 times 4, because 4 times 4 is 16, but it doesn't divide 4. But we can do this with primes. So, let's take the proof. We're going to do this by induction on n. So for the base case n equals 2, that means that p is dividing the product of two numbers. So, we have two cases. Either p divides a1 or p divides a2 by this lemma. So if p divides a1, then, we're done. So we have to think about the case where p doesn't divide a1. We can do this without loss of generality. I could switch a1 and a2. And so we let g equal to the GCD of a1 and p. So as we saw last slide, since p is prime, well, the GCD of a1 and p is either going to be 1 or p itself. But we can't have g is equal to p itself, or otherwise it implies that p divides a1, and we assume that p doesn't divide a1. So we know that the GCD of a1 and p is equal to 1. And so by result that we proved the last video, that implies that p divides a2. Remember that if a divides bc, and GCD of AB equals 1, then we must have that A divides C. That's a result we proved last time, and we did that with Bazoo's lemma. We can get back to that if you want. And so that is proving for us the base case, because we have a P divides A2, and in the other case, that would just be P divides A1. So now we take the inductive step, and we assume that the lemma holds for nk that's bigger than 1. And so we'll show that if the lemma holds for k bigger than 1, then it must hold for n equals k plus 1. So we're going to let big A equal to the product A1 times A2 times all that times AK. And so then A1 times A2 all the way up to AK times AK plus 1 is just big A times AK plus 1. So we've reduced this k plus 1 fold product to a 2 integer fold product. And so thanks to the base case, we now know that if P divides, A1, A2 all the way up to AK plus 1, then it either divides big A or AK plus 1, because we proved the base case for any 2 integers. So in the case where P divides big A, well, then that means that P divides A1, A2 all the way up to AK. And the inductive hypothesis tells us that then that means that P must divide one of these constituent products. So that's what the inductive step is for. And otherwise, P divides AK plus 1. So we've got that either P divides one of A1, A2 all the way to AK, or P divides AK plus 1. And so that completes things, right? It's in the end, it divides all of, one of the constituent products of A1 times A2 all the way up to AK plus 1. So thanks to the principle of mathematical induction, once again, the proof is now complete. So we proved the lemma, and now we can prove the fundamental theorem of arithmetic. And arithmetic is Gauss's name for elementary number theory, so this is the fundamental theorem of elementary number theory. So, and this theorem says that every positive integer can be written as a product of primes with possible repetition, and that any such expression is unique up to a rearrangement or a permutation of the prime factors. So that means that I can take any natural number, and I can write it as a product of primes uniquely, up to a rearrangement of a product. But since products commute, when we say a unique product, we already kind of assume that. And notes that, we're going to take 1 as being the empty product, similar to how 0 is the empty sum. And if you don't like that, you could just rethink about this theorem as saying that for every integer that's bigger than 1, it can be written as a product of primes. It doesn't really matter. So let's take some examples. 15 is 5 times 3. 5 and 3 are prime. 100 is 2 squared, which is 4, times 5 squared, which is 25. 4 times 25 is 100. And 2 and 5 are primes as well. And then for a little bit of a harder example, 1, 2, 3, 4, 5, 6. Well, 123,456 is equal to 2 to the 6, 2 is prime, times 3 times 643. And yes, 643 is prime. You can try and check that for yourself. So this proof is going to have 2 parts. First, we need to prove the existence, that such a factorization actually exists, that there's no numbers that cannot be written as a product of primes. And that's already, a big step to show that all natural numbers are expressible as a product of primes. That's already a really important result. And then we can also prove that it's unique. So that that product of prime can only be written in one way if we arrange the primes in a predefined order. So let's first prove the existence of this. And it's going to be one of our classic well-ordering principle contradiction proofs. So we're going to let the set S be a non-empty set of positive integers that cannot be written as a product of primes. So since we're assuming that it's non-empty, we're going to say that it has the smallest element n by the well-ordering principle. And so, we want to get to a contradiction and show that this set doesn't exist, that it is empty, and so that there is no positive integer that cannot be written as a product of primes. That's our end goal. So m is not equal to 1, since 1 is the empty product, right? So 1 could not be an S. And once again, if you don't like this idea of empty products, even if we reformulate the theorem to say all integers bigger than 1, then m would also not be equal to 1. So we know that m is not equal to 1. So m is at least bigger than 1, it's a positive integer. We also know that m is not a prime. And why do we know that it's not a prime? Well, if it were a prime, it could be expressed as a one-term product, just itself, right? And so that would be a product of primes. So m has to be a composite number. So m is expressible as a times b, with a and b are bigger than 1. And so we have that a and b are smaller than m. So by the minimality of m, a and b cannot be in S, right? Because m is the smallest integer, the smallest element, of S. So by definition, that means that a and b can be expressed, as a product of primes. Because if they're not in S, then, since S and S knots partition the naturals, well, they have to be expressible as a product of primes. You either are or aren't expressible as a product of primes, so it's pretty simple. But if a and b are expressible as a product of primes, since m is equal to a times b, then it's also going to be expressible as a product of primes, right? So that's a contradiction, because it can't be in S. And so S has to be empty. And that's actually all we need to do. It's actually a pretty simple proof by contradiction, but that's when you see that such simple tools are really, really powerful. And so now we can also prove uniqueness. And so to do that, it's actually going to be a sort of the same type of proof. We're once again going to take a set S, and this time it's going to be the non-empty set of all positive integers that can be expressed as a product of primes in 2 or more different ways. So we first had to prove existence, right? Because, we first have to show that all integers can be expressed as a product of primes. And now we want to take the set of integers that can be expressed as a product of primes in 2 or more different ways. And we want to see that that's not possible. So by Wahl-ordering principle, S is going to have a smallest element m. And so that's m is going to be p1 times ... times pr, right? So p1 times p2 times p3 all the way to pr. But it's also going to be equal to q1 all the way up to qs. And this is where all of those p's and q's are primed, right? And so the fact that it's in S means that these two products here are a difference. So we've got some qi which is not equal to any of the p's in here. And so what we want to show to get to our contradiction is that R is equal to S, so that they have the same amount of prime factors first, and then that the string P1 all the way to PR is a rearrangement of the string Q1 all the way to QS. And so note that here we're talking about a product. So this is P1 times P2 times P3 all the way to PR. While here we're talking about a string, so a sequence in some sense, right? And so P1 divides M, that's just pretty simple, which is equal to Q1 all the way times QS. So now we can apply our lemma that we proved earlier to see that P1 must divide one of the QIs, with I is in 1, 2, all the way up to S. But since P1 and QI are prime, we must have that P1 equals QI, right? Because primes can't divide primes, otherwise the other prime wouldn't be a prime anymore. So if P1 equals QI, we can cancel them from this product here to get P2, so we've canceled P1, times P3 times P4 all the way to PR, is equal to Q1 times ... all the way to Qi minus 1 times Qi plus 1, so I've removed Qi, and then we keep multiplying until we get to Qs. And note, I could have I is equal to, don't get confused here that Qi is not equal to S or 1. We could not have this Q1 or this Qs. It's I here is a general number in 1 to S. This is just so I can represent it easily. So since this number is smaller than n, because we've canceled a prime out and the primes are not equal to 1, then it can't be an S, right? But because m is the smallest element in S. So that means that r minus 1, because keep in mind the length of this product here is r minus 1, and the length of this sequence here, of this product here, is s minus 1. So since these guys are not in S, then this here is an integer that can only uniquely be represented as a product of primes, right? Otherwise it would be an S. But if it can only uniquely be represented as a product of primes, then these products must have the same length. So that's what we're saying here. And similarly, these products must be rearrangements of each other, which is why I'm saying here that the string P2 all the way to PR is a rearrangement of the string that we have here. Although here's the product. And so now I can just add 1 to this equality to get R equals S. And I can just remultiply by P1 and by Qi, reintroduce them into the sequence to get that these are rearrangements of each other. And so M then can't be an S because we've shown that these two products are actually equivalent. And so that means that we've got a contradiction. And so there is no such set S. So now we can get to our second really important theorem about primes. So we've shown that primes are the building blocks of the natural numbers. And so now you might ask yourself, there's infinitely many natural numbers, but are there infinitely many primes? Primes are building blocks of natural numbers, but maybe you can get really lucky. Maybe there's only a few primes that actually characterize everything. Unfortunately, there aren't. There are infinitely many primes, and that's what we're going to prove here. And it's also cool that there are infinitely many primes. It is a useful theorem. So that's what we have to prove that there are infinitely many prime numbers among the natural numbers. So we're going to see two different proofs of this. One of them by Euclid, and another formulated by Euler. So let's first look at Euclid's proof because it's relatively simple. So we suppose that there are finitely many primes, p1, p2, all the way to pn, if n is bigger or equal to 1, right? So we know all the primes, and there are finitely many primes. And so we want to get to a contradiction, obviously. So we're going to consider the number n, which is equal to all these primes multiplied by each other, added 1. All right? Well, n is obviously bigger than 1, and so by the fundamental theorem of arithmetic, there is a prime, pi, such that pi divides n, because n can be expressed as a product of primes, right? So we've got that one of these p's divides n. But if we use the Euclidean algorithm, right, the greatest common divisor of pi and n is the greatest common divisor of pi and 1. And why is that? Well, we showed earlier that the GCD of a and b is the same as the GCD of a and the remainder of b divided by a. And the remainder of n divided by pi is easily seen to be 1 here, because we've got pi times all these other primes, and then we add 1. So the remainder on division by pi is 1. And the GCD of anything with 1 is just 1. So that means that pi does not divide n, because they're coprime, right? If they weren't coprime, then if this pi did divide n, then they can be coprime. And so that's a blatant contradiction, because we just said here that pi does divide n. So the list p1, p2, all the way to pn was not exhaustive, and so we can generate a new prime. It turns out that n here, if these primes were ordered, and we included all the primes smaller than pn, then this number n here would actually be a new prime number. And if we didn't, then then the pi that divides n would be some prime number that we haven't included. So now we can look at Euler's proof for the same thing, but there are some prerequisites to Euler's proof, and notably the geometric series, which states, well, the infinite geometric series that states that if k is bigger than 1, then the series 1 over k to the I, so I add 1 over k to the I as I gets bigger, converges to 1 over 1 minus 1 over k. And so more generally for geometric series, we have that a times k to the I for any k, summed from I to n, gives us a times 1 minus k to the n over 1 minus k. And so you could take the limit of this as n approaches infinity and see that it diverges if k is bigger than 1. And it diverges if k is smaller than 1, sorry. If the absolute value of k is smaller than 1. Because in this case here we have k to the I, here we had 1 over k to the I. Diverges, and otherwise it converges. And another prerequisite is namely the harmonic series, which states that the harmonic series diverges. And the harmonic series this is 1 over a, it should say 1 over I. The harmonic series is simply the series of 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. And it might not be so clear that doesn't converge to a number, but it diverges. So we're going to use these two facts, and if you're not familiar with them, then maybe just skip this part entirely. So, Euler's proof. We're going to suppose, once again, that there are finitely many primes, p1, p2, all the way to pm, and this is the exhaustive list of all primes. And so by the fundamental theorem of arithmetic, any positive integer n is equal to p1, well, some power of p1 to the e1, times p2 to the e2, all the way times pm to the em, with all of these e's bigger or equal to 0. And if I don't want to include any of these primes in the factorization, I can just set equal to 0. So now consider this big old thing, the product, a capital pi, which is going to be equal to 1 plus 1 over p1 plus 1 over p1 squared plus 1 over p1 cubed plus 1 over p1 to the 4 and so on. And that goes on to infinity. Times 1 plus 1 over p2 plus 1 over p2 squared and so on. And this product goes along across all these primes so that we end up getting 1 plus 1 over pm plus 1 over pm squared plus 1 over pm cubed and so on. That's a big old thing. It's a much more complicated number than the n we had in Euclid's proof. So first of all, note that each of these terms here is a finite number. And this is due to what we saw in the last slide, which is the infinite geometric series. We have that pi is bigger than 1. So the sum of 1 plus 1 over pi plus 1 over pi squared and so on converges to the integer 1 over 1 minus 1 over pi. So we have to do this step just to show that pi is a well-defined finite positive number. This isn't some kind of thing that is going to diverge, because we've got a finite product of finite integers. And so upon expanding pi, I say finite integers on finite numbers, sorry, these aren't necessarily integers. So now upon expanding pi, let's try to think about what happens when we expand this product, right? And we're going to use this doing the good old FOIL technique. So, if you do a plus b times c plus d, if you FOIL this, which you might have learned in high school, you get a times c, right, plus a times d plus b times c, and finally plus b times d. So all we're doing is we're taking all possible combinations across these two things, right? And so here it's more complicated because we've got a bigger product and we've got bigger constituent parts. But we can actually apply the same logic. One of the terms we're going to get in the final sum is going to be, for example, 1, because I know I can take 1 here, I can multiply it with 1 here, and multiply it with a 1 here, and all the ones that are in between, right? What I could also do is note that I'm going to have 1 over p1 times 1 over p2 times 1 over p3 times all the way up to 1 over pm. That's also going to be one of my terms. And in fact, I can actually do this with any of a combination of these constituent parts. So that in the end, I'm going to end up characterizing all the terms as being 1 over p1 to the e1 times 1 over p2 to the e2 times ... times 1 over pm to the em for any n, right? So any of the terms, all of the terms are going to be all of these combinations of products of the reciprocals of the primes, well, powers of reciprocals of the primes. And so since the fundamental theorem of arithmetic tells us that any positive integer is represented by this, this means that all of the terms are actually going to be all of the positive integers, because I'm going to get all of these products here. And I wrote n here, it should say 1 over n, all of reciprocals, right? Because this bottom product here distributes, so I get p1 to the e1 times p2 to the e2, all the way times pm to the em, for all possible combinations of these powers. So that means that, when we distribute, we're going to get a sum in the end of all these types of terms. So big pi, capital Pi, is going to be the sum of the reciprocals of all positive integers. But, if big pi is equal to the sum of reciprocals, that's what this here is saying. Well, we saw in the last slide as well that the sum of reciprocals is, it's the harmonic series. But when you have an infinite sum of reciprocals like that, that diverges. So pi is not well-defined, but we said that it was well-defined here. And so that's where we get our contradiction. We managed to prove first that pi was finite, and then we managed to prove that it wasn't. So, that's a contradiction, and that is the end of Euler's proof. And so it's definitely more complicated than Euclid, and if you want to prove in general that there are infinitely many primes, you should probably go for a Euclid's proof. But Euler's proof is very important in other contexts, and notably it helps us in proving that the sum of the reciprocals of primes diverges. But we're not going to look at that. And so now I want to look at one final thing on primes, now that we've proved all our theorems before we end. And that is, I don't know how we pronounce this, I think it's the sieve of Eratosthenes. Please correct me if you know how to pronounce that well. And it's a technique to quickly find primes, and namely it does it in square root time. So if I want to find all the primes that are smaller than n, well, it only takes me a maximum of square root of n steps. So we're not going to prove the validity of this algorithm, but we're simply going to do it by intuition. So what I do is I start by crossing out 1, because 1's not a prime. And so I go to 2. So this is, by the way, this is finding all the primes smaller than 100. So I know that 2 is the smallest prime, right? So I circle 2. And what I say is, let's remove all multiples of 2. So I remove 4, I remove 6, I remove 8, I remove 12. So I remove all even numbers, right? I cross all of them out. And because, they're going to be products of the prime 2, so they can't be primes themselves. Then I get to 3. And I note, well, if 3 wasn't a prime, then it would be some product of 1 or 2. Well, specifically 2, because, the products have to be bigger than 1. But we just said that 2 was a prime, and we just crossed out all multiples of 2. So 3 is not a multiple of 2 since it wasn't crossed out, right? So 3 has to be a prime, because all the numbers smaller than it have either been crossed out, or they were primes themselves. And so now I can circle 3, and I can cross out all the multiples of 3. So 6 was already crossed out, but 9, for example, wasn't. 12 was already crossed out, but 15 wasn't, and I go on. And so then we keep going on. 4 is crossed out, we skip 4, then we get to 5, and we note that all the ones smaller than 5 are either crossed out or primes themselves, so 5 is itself a prime. And we cross out all multiples of 5, and that's pretty easy, I can just go down this row. And I keep going, and I get to 7, and there's still a few products here that haven't been crossed out, so I can cross out 49. And then 8 and 9 have been crossed out. And so actually, that's enough. And I'm supposed to have all the 10s here. I don't know why I think I've messed up on my animations, but whatever. Once I reach 10, and 10 has been crossed out, we actually have characterized all the primes smaller than 100. Because note that if any of these integers that haven't been crossed out yet, so let's say 53, for example, if 53 hasn't been crossed out, let's imagine 53 wasn't a prime, right? Well, yeah, if 53 wasn't a prime, then it would be expressible as, some product of 2 integers that are smaller than 53. And keep in mind, those integers, well, one way we can express 53 as a product of 2 numbers is square root of 53 times square root of 53. But so now that means that if I take any product of 2 numbers that's equal to 53, one of those numbers has to be smaller or equal to the root 53, and the other one has to be bigger or equal to root 53. But we've shown that all numbers that are smaller or equal or bigger, that are around root 53, are primes, or because root 53 has to be smaller than 10, because root of 100 is 10, and we've already characterized all the primes or non-primes that are smaller than 10. So it means that 53 can't be expressed as such a product, because we've crossed out, all the products that would have been made by these numbers. And so that's why we get all the ones up to 100, because 100 is 10 squared. And if I went all the way and did this process to up to 23, for example, then I've characterized all the primes smaller than root of all the primes, smaller than 23 squared. And so that's the see that Aristotle used. And one way to see it better is to get rid of all those crosses. And so, that's where we see all our primes. And one thing that's striking is how random this distribution seems. We've got all the primes smaller than 100, and I guess you could repeat this for a bigger square, because 100 maybe is a little small. But, if I was to do this with even numbers, or the powers of 5, or whatever, you'd have some clear pattern. Here, it seems very... weird. It's very sparse, and actually, that's one of the characteristics of prime numbers is they seem to have a very sparse distribution, but this distribution does have some structure as you start to increase the number of primes that we're considering, and so we're not going to look at exactly what this distribution is, because proving that distribution, it's called the prime number theorem, is way over the scope of this course. I don't even know what the proof is. I just know that it's not part of elementary number theory and requires a lot more stuff. But it's an interesting thing to keep in mind. And so now that we're done with primes, in the next few videos we're going to be considering problems that have to do with counting, because this is elementary number theory, the study of counting numbers, so we want to be able to know how to count. And so we're going to get into the complex field of combinatorics. See you then.